between, I may ask some questions or some comments from your side to get the idea how much familiar you are already, or do questions in line with GATE exams? That is a good question. See, this is NPTEL course. So here, basically, we will try to cover entire area of electrical machines, and NPTEL must, sorry, GATE must be a subset of whatever you will learn here. So give more questions in session. Yeah, definitely. Our job is to provide more questions and all. So for the, yeah, it will be in line with GATE. If you can solve all these problems from assignments and quizzes and whatever we are discussing, I hope you will be able to solve all those questions. Okay. So let me start with the, screen. So I hope my screen is visible to you guys. Uh, could anyone please respond if whether my screen is visible or not? It is visible. Yeah, thanks. Yeah, so I hope you are able to see the first question. Okay, it is very basic question, and here wire is carrying a current, and we have to identify the direction of flux in that wire. So we have to identify which direction of flux is correct. Okay. Anybody could unmute himself or herself and please try to answer because this is very basic. And if it is not clear, then uh, we will go much. We will go to much basic level. Okay.
Diagram theory only. Option number.
Option number D. Okay. So someone has told option number D, diagram 3. So yeah, it is correct. And how it is correct? You place your thumb in the direction of current and you curl your fingers, and whichever the direction your fingers will follow, that will be the direction of flux. Okay. So according to this, option 3 is only correct. Means option D is only correct. Diagram D. So if you keep your thumb in this direction and if you curl your finger, So it will be moving in anti-clockwise. Okay, so I hope it is clear. Anyone has doubt for this? Okay, so I'm moving on. If nobody has any query related to this. So this second problem is related to some formula and all. So we will revisit this problem. Okay. So for time being, again, another basic problem related to direction of flux you have to identify. So here you can see that current directions are denoted with dot and cross, and you have to identify the direction of magnetic field. So here again, you have to choose one option and tell us the
Option number A.
option A. Option A, it is diagram 1 only. Yeah, that is correct. Because if you keep your thumb in the direction of current, which will be upward, and you curl your finger, so you will see that flux will be anti-clockwise. So let's see what about diagram 2. Diagram 2 is just opposite of diagram 1, so it is wrong. And in diagram 3, you have to place your thumb downward, and you can see that flux will move in clockwise direction, and here it is denoted with anti-clockwise, so it is wrong. So yeah, Samir, it is option A. A is correct. Now coming back to fourth problem. So here you observe it very carefully, okay, and you have to tell which diagram has the correct direction of magnetic flux. Okay, so we all know that magnetic flux originates from North Pole and goes to South Pole, and along with that, you have to take care of the direction of current. Okay, so both the direction of current at each corner you should observe along with the direction of flux, whether they are coming from North Pole or South Pole. So you have to take care of both the things. So go ahead and first you tell me an answer with an explanation, and then I will discuss this. Anybody? Anyone knows the answer of this problem? Please raise your hand. Okay, so what about the diagram 1? Diagram 2, Kapil has told diagram 2 is correct. Okay, so Kapil, could you please explain as well how the diagram 2 is correct? Yeah, Kapil, go ahead, please. I think you have unmuted yourself, but I am not able to hear you still.
Sir, please show me a whole question, sir. A statement is not visible, sir.
Okay, okay. You should have told it earlier. Is it fine now?
Yes, sir. Okay, thank you, sir.
Yeah, welcome. Magnetic
Sir,
lines. Huh, go ahead, please.
magnetic lines created from the end pole outside the area and enter the
Huh.
S pole, and the inner side create the fluxes S pole and passing through towards the end pole. In the I mean, lines like so that
Haha. I
the magnetic flux is created from end pole outside the area, and
mhm.
inner outside the end pole to S pole.
Okay, so which one do you think is following that according to your statement? So you told that magnetic lines should originate from North Pole and it should enter the South Pole. That is correct, but which diagram it is following?
Mm. The diagram number second.
Diagram number
Diagram number
second.
second.
Okay, this one.
Yes, sir.
Uh, Here, if you see the flux direction, it is coming out of the South Pole and entering the North Pole. Okay, and that is correct. And another criteria it should follow that the direction of current. Okay, direction of current, if it is upward, near to the, if you see, let me highlight it. If direction of current at this point is upward, right? And if it is upward, you place the thumb in that direction. And if direction of flux is following the same direction, then both conditions are met and then our option should be correct. Am I right? If you see that the current which is flowing through the wire, uh, that is extruded, you imagine it as extruded in the z direction. Okay, and at the corner, at this corner where I have highlighted with red color, if you place your thumb and if you curl your fingers, other four fingers, then you will be able to see that they are following the path. Okay.
Sir, this rectangular things is a material or not, sir?
They are magnetic material. They are obviously magnetic material.
Then above this, there is South Pole, and below this, there is North Pole. Is it like,
Yes.
sir? Okay, thank you, sir. Now I understood.
Okay. Okay. So first you should try to understand the question. If it is not clear, you should ask. Okay. I appreciate what's your name? Who just clarified the doubt?
Ayush Aniket, sir.
Ayush. I appreciate Ayush. He clarified his doubts. So you should clarify first whatever, whether you are able to understand the question or not. I can repeat the question multiple times and then you can observe this. Okay. So, yeah, uh, the magnetic flux here, if you verify that diagram too, it is following. And if you observe anything from on diagram, but diagram 2 has a problem with the direction of flux. Here the magnetic flux is coming out from the South Pole. You can see magnetic flux is coming from the South Pole and entering to the North Pole. But instead, I mentioned that magnetic flux should originate from North Pole and enters into South Pole. So that condition is not met here. Am I right?
Yes, sir. But inside the material, the flux is flow from the south pole to the north pole, no, sir?
Okay, so you are saying that in air gap, it should flow from north to south, and
Yes, sir.
inside it should follow the south to north. Okay, so anyone is agreeing with Ayush? Whatever he just mentioned, in air gap, flux should originate from north and enter south, and in magnetic material, it should. Sorry, I couldn't get you. Swapnil, you are trying to say something? Okay, so this one concept is very important. We mute him. So you have to take care whether it is an air gap or magnetic material. Okay, so Ayush is right. In magnetic material, it diagram 2 is following the correct characteristics of flux lines. Okay, and if you see from diagram 4, it is just opposite of diagram 2, and you can be confused with the option of diagram 2 and diagram 4 very easily. So here you see that in magnetic material, this flux is coming from north to south, what I just said, and it is following the same. So if you keep this concept in your mind, then you will be able to pick the right answer. So here, diagram 2 is correct option B. Okay.
Yes, sir.
Anyone has any doubt in this problem?
No, sir.
Okay. So if not, then I will move ahead. Okay. So another problem is related to again magnetic flux and magnetic core. And here you can see that which way magnetic flux would flow in the core, as you can see the wires are carrying a DC current. Okay. So I have got answer clockwise.
So number A, sir.
Number A. Yeah, you are correct. Number A. So a wire is carrying a current, and you can curl your fingers in that direction, and you can see that flux will be confined to this core in this direction. Okay. So option C. Okay. Samir, you mean clockwise, not C, right? Okay. So anyone has any doubt, they can raise their hand. Otherwise, I will move on to the next problem. Okay. So in sixth problem, we are given a core with three turns, and three different turns have their own different number of turns, and in each coil, in first coil, the voltage is given as a 300 volt. Here V1 is equal to 300 volt of AC, and two voltmeters are connected across other two coils. Okay, and here you need to identify the voltage values. Okay. So voltage across second coil V2 and voltage across third coil V3. And if you know the relationship of turns ratio or transformation ratio, you might have gone through the lectures, so you might be knowing that E1 by N1 is equal to E2 by N2 is equal to E3 by. This is the expression of an ideal transformer. Okay. So how many of you do not know this expression? If you don't know, please raise your hand so that we can discuss this concept.
Sir,
Or
option
if
number C will be correct answer.
option number C, okay. So for time being, I am checking option number C. We will revisit this. Yes, transformation ratio or whatever you say, transformation ratio, turns ratio. Yeah, so if you apply this expression, I think everybody must be aware to this expression. So if you apply this expression, then you can get V2 by V1 is equal to N2 by N1, and N2 and N1 is nothing but 300 and 300. So V2 will be V1 into 1. So V2 will be 300 volt, which is given in option C and option D. Okay.
It's correct,
And
sir. E2 is equal to 300 and E3 is equal to 200.
that we will check about V3 now. We are just moving slowly so that everybody can grasp it. So now V3 by V1 is equal to N3 by N1. If you apply, then you can get V3 is equal to N3 is nothing but 200 and N1 is nothing but 300. So it will be 2 by 3 into 300. It is 200 volts. So option C is only following the criteria, right? So option C will be correct. Anyone has doubt in this? Okay. If not, then we will move on. Yeah, go ahead, please. Okay, so I am moving on to the next problem. It is again similar problem, but here at the place of voltage, we are given with the current. So we have to take care of MMF balance or power balance, right? So here V1 by V2 is equal to N1 by N2 as we saw earlier. Now, in an ideal transformer, if you assume that MMF is balanced, then N1 I1 is equal to N2 I2 is equal to N3 I3. Okay. So now I1 by I2 can become N2 by N1. Okay. And I1 by I3 can become N3 by N1. Okay. So here we need to identify what should be the value of I3 such that flux in the core should be equal to 0. Okay, so we will add all the MMF and they should be equal to 0. So let's start doing that. N1 I1 plus N2 I2 plus N3 I3 is equal to 0. Okay, so it is just like KVL you must have applied in a loop, in a closed loop. It should be equal to 0. And here also the summation of MMF of all the terms should come out to be 0. Okay, so we have given with N1 which is 300 into I1 which is given 1 ampere plus N2 is 300 and I2 is 3 ampere plus N3 is 200 into I3 is not given, which we need to find out. Okay,
4 ampere, sir.
4 ampere. Okay, we will see what is it. So
4.5,
200
sir.
okay,
Sorry.
okay. We will see what it comes
Okay,
out to.
4 ampere, sir.
Is equal to, I am sure it should come in minus, right? It should be in negative. Minus 900. So I3 will be minus 1200 divided by 200. So it will come out to be minus 6 amperes. So I3 should be minus 6 ampere, but we should not conclude here. We should verify whether the direction of flux is correct or not. So from N1 I1, the flux will have the tendency to flow in clockwise. From N2 I2, again flux will have the tendency to flow in clockwise. And from N3 I3, again the flux has the tendency to flow in the clockwise. But to maintain the zero value of flux in the core, either you should reverse the winding of third coil or you should reverse the direction of current in the third coil. Okay, so here winding is already decided, winding configuration is already decided, so we have only thing in our hand is current direction, so we can reverse the current direction and it should be 6 ampere. Is it fine?
Yes, sir. Yes, sir.
Okay, great. So if any doubt is there, feel free to ask, otherwise I will go on. Okay, so again here, this is another problem related to transformer. Okay, so in this transformer, the core flux will be 0 if which condition it will satisfy? A, B, C, D, or E?
C, sir.
C. Core flux will be 0 if N1 is equal to N2 by 2. If N1 is equal to N2 by 2, then you are saying that core flux will be 0. Does anyone disagree with him?
Option number A, sir.
Option number A. Another. Any other option anyone has in their mind?
B.
RD B. N1 is equal to 2 N2. Okay, so we have got 3 options. And okay, so I got 3 answers. now, three of you, could you please justify your answer? Why did you choose A, B, or C?
Sir, the flux will be not be zero, sir. In the
Sir, supply
No, no.
direction.
Please go one by one.
Supply.
Option A, who has marked? Please speak up.
Yes, sir.
Go ahead.
Sir, I have used the MMF balance equation for
Okay,
the.
so I will. Okay, so I will come back to you later. Option B, who has marked? Please speak up.
Option A is correct now.
No, I will comment on this, but first you should explain your justification. That why did you go with option B or C? It is fine. It is just discussion. We are discussing here. You might have something else in your mind. So go ahead with your.
Sir,
Huh.
if you apply the right hand rule on the N1 coils, we can see that the thumb will point towards the upper direction. That is, the direction of flux will be upper for the N1 coil.
Yes.
Yeah.
Yes, that is correct. And now to maintain
Similarly,
Go ahead.
if you apply the right hand thumb rule for N2 coil, the flux will be as seen above, like that, going upward.
Okay.
So both the fluxes will cancel. Then N1I equal to N2I. This implies N1 equal to N2. I will be cancelled.
Okay, so here N1 I1 plus N2 I2 will be equal to 0. And hence,
But I1 and I2 are equal. I1 and I2 are equal now.
Because they are both connected with the same wire, you can see, right?
So they will be
current
equal.
will be same in both the wire.
Yes.
Okay, so I'm clarifying it. So option A is correct.
Sir, there is some echo sound, sir. Please.
I think it is coming from the last person who was spoken. Who was the last person who was speaking? Who was justifying all N1 I1 plus N2 I2 is equal to 0? No, I am not saying anything. You just, after speaking, turn off your mic. Okay. So again, ninth problem is similar to eighth problem, but here we have, or we are required with finite flux in the clockwise direction. So we need some flux in this direction. Okay. So
Sir, please.
Yeah.
Please tell me about previous question, sir.
Okay, this one.
Yes, sir. Which one will be correct?
Okay, so option A is correct. As that guy just clarified. See, if
Okay, sir. Okay, thank you.
if the current direction is in such a manner which is provided earlier, and both the windings are connected with the common wire, right? And if you see from the coil 1, the flux direction will be in the clockwise direction, and from coil 2, the flux direction will be in anti-clockwise direction. So the direction of current and windings are proper to cancel each other, right? We just now need to make sure that magnitudes are also equal. To make the equal magnitude, we need to, N1I is equal to N2I. So N1 must be equal to N2. Am I correct?
Okay, yes, sir.
Okay, so I hope now you get it.
Yeah. Thank you, sir.
Okay. What about the option always?
What about the option always? Okay, so yeah. So if N1 and N2 are would have been given with N, right? Then it would be always 0, right? If let's suppose in the problem, if instead of N1 had been given with n, sorry, and n2 must have been given with n, then you could have chose the option always, right? Because currents are also equal, number of turns are also equal, and direction are opposing each other every time. So in that case, they will always cancel each other, no matter how much turns you increase, that no matter how much current you increase, it will always cancel each other and it will be zero. Did you get it?
Yes, sir, thank you.
Yeah, welcome.
Hello,
So
sir.
Yeah, go ahead.
Sir, this class will be recorded available on the NPTEL website.
This is recorded. You can find the recording in the same Teams meeting link or same Teams chat, as well as you will be shared with Excel sheet where all the recordings will be available. Okay, and that mail will come from NPTEL side. Okay, so you just
Okay, thank
keep checking your mail.
okay, thank you, sir.
So in ninth problem, I am again going with the ninth problem, which is similar to eighth, but here the condition is bit different. Here the requirement is that core flux should be finite and in clockwise direction. Core
Option B,
flux
sir.
should be option B. Okay, we will verify each and every option. So
N1 equal to 2
N1 is equal to 2 and 2. So he's saying N1 is equal to 2 and 2, then the flux will flow in the clockwise direction.
Yes, sir.
Okay, so the windings are same, current directions are same. It's just that we have to flow the clockwise direction. So okay, option number C. Who told option number C?
I am, sir.
Okay, Ayush told option number C. Who told option number A?
Atul.
Atul.
I also
Okay.
go with option B.
Option number B, Lavanya.
Yes, sir. Actually,
Sir.
N1 equal to 2, N2 is option B.
Okay. First one is option B. Okay, so both are with the same option B. Okay, so yeah, to make the finite flux in the core and that too in clockwise direction, we must ensure that MMF of the primary winding should be higher than the secondary winding, right? And to make sure, we must see that N1 is always greater than N2. Whether it could just by 1 turns or just by 1 ampere, but here you couldn't change the current. So you have only the degree of freedom in number of terms. So, and if you observe all the options, only option B is satisfying that condition, such that your MMF from primary winding is higher than the secondary winding. Right? So option B is correct. And Ayush, could you explain why did you go for option C?
Sorry, sir. It is misconception.
Okay, so you misjudged the condition. Okay, fine. Now again, we are going with the similar kind of problem in 10th question. Read it carefully. And here, when the core flux will be zero, we have to find out the condition when the core flux will become zero. Okay, any guess?
Never become zero.
Never, sir.
Never. So Option E, you guys are going with, and let us see whether it is correct or not. So N1 I1 is going in this manner, and because of N2I, flux will go in this manner. So whatever is the number of turns, it will always have some finite flux, right? Since current is not equal to 0, it is already mentioned. If current would have been 0, then core flux may become 0, but here current is also non-zero, so there are no chances that it will be 0. So yeah, so we have always a condition with the flux flowing in the clockwise direction. So option A is correct. Okay. Does anyone has any doubt with this?
Sir, can you explain, sir, 9 number question again, sir?
9th number. Okay. See, here the output we want as core flux should be finite and in clockwise direction, right? So because of first winding, you can see that flux is flowing in clockwise direction, right?
G, okay.
And because of second winding, you can see that flux is flowing in the anti-clockwise direction.
Direction. Okay.
Now the tendency of secondary winding is to oppose the primary winding MMF or
Yeah.
flux
Yes.
originated due to MMF. And if we want some finite flux in the clockwise direction, we must have higher value of primary winding MMF compared to secondary winding, right?
Yes, sir. Yes.
And that condition can only be fulfilled if N1 is higher than N2.
Yes. Yes.
Did you
Yes.
get it?
Yes.
And that
G.
is given in option B only. So we are going with option B, and you cannot change the current of primary winding because both the windings are connected with the same wire. So currents in the both wires will be same.
Yes. Yes. Yes.
Yeah, so that's all. And did you get the 10th question, Rajesh?
This question will be understand, sir.
Okay, so here the condition was we have to maintain the core flux 0, right?
Yes, sir.
And if you see that direction of flux because of primary winding, so from primary winding you can see the direction of flux. Just give me a minute. Okay, so due to primary winding, you can see that the flux will flow from primary winding, it will be clockwise, and from the secondary winding, you can see that flux will flow again in clockwise, right? Rajesh, are you with me?
Yes. 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 G, sir.
Okay, so here flux will always flow in the clockwise direction, and whatever the number of turns you can set, it will be always in the clockwise direction. So you cannot maintain flux 0 in the core.
Okay,
Did you
sir.
get it? So that's why two people told that it will be never, core flux will never become 0, right? So, and they were, I guess, Ayush and Atul. So
Okay.
does anyone have doubt in this problem still?
Sir, under the C condition, will the flux become negative?
Flux become negative. Okay, so flux direction you can identify. You mean flux negative, that will mean that either clockwise or anti-clockwise. Okay, flux is a, you know,
So,
it
here,
is
like
based on
the number of
sorry.
based on the problems we discussed earlier, like in order to have clockwise flux, we should have N1 turns greater than N2. But according to C option, when we go for that one, I hope N1 number of turns will be less than that of N2. So that anti-clockwise flux will be higher, like MMF will be higher. So that will be dominating. I'm just interested
Okay.
in knowing what
Okay.
will happen when we go for C option.
Okay, so let us suppose we have C option. We have condition given with C option, right? So according to you, in the C option, N1 is equal to N2 by 2, right? So here N2 is higher than N1, correct? And if N2 is higher than N1, then you can see anyway, because of N2I, the flux will flow in clockwise direction. And because of N1, the flux will again flow in clockwise direction. It's just that flux coming out of because of primary winding, the magnitude of the flux will be less compared to the secondary winding. Okay, the contribution from secondary is higher than primary if option C is there. But again, the flux will always flow in the core in clockwise direction. Did I get your question correctly?
Okay, sir, I got my explanation. Thank you.
Okay. Or to make it zero, either you have to make current equal to, you have to reverse the direction of current, or the winding pattern you need to reverse it. Then it can become zero. So make it zero, you must make sure that both winding MMF are provided in such a manner that flux originated from those windings are opposing each other. So as we will go deep in transformer, dot polarity and all concepts, we will be able to visualize how they behave, how they oppose, and basically from the operation of transformer, it will be very easy to visualize all those things. And anyway, you will be able to see those concepts in lectures also. So I hope you follow all the weekly lectures by the professor. So in 11th problem, it is again wound in similar fashion, but here the requirement is core flux should be finite and in clockwise direction. Okay. So here you
Always,
can,
sir. It's
it is always you are saying. Okay, so I use told option B. Anyone else? Anyone else is with option D, or anyone has any different idea?
Sir, option D.
Option D. Option D. Okay. So, okay, let us verify. Now, here, because of primary winding, flux will flow in the clockwise direction. And because of secondary winding, flux will again flow in clockwise direction, and current is not zero. So it doesn't matter whether N1 is equal to N2 or greater than or less than N2, flux will always flow in the clockwise direction. So it will always flow. So option D is correct. Okay. Does anyone have any doubt in this? Okay, I'm guessing everyone is fine with this. So we will move on to the next problem. Now the type of question has been changed, and you can see you need to recall some motional EMF concept and all basic 12th class concepts of physics so that you can apply. So first you read the question carefully. Okay. Here a straight conductor is given with length, okay, and it is moving with the velocity of 5 meters per second in z direction, and you can see that intensity of flux density is given with 0.8 Tesla. Okay, and you need to evaluate the EMF, how much it will induce in the conductor, or what is the direction of the EMF.
Sir, EMF will be 8 volt.
EMF will be 8 volt.
8 volt and directions will be from X to Y.
From X to Y. From X to Y. Okay. So first let us talk about the which formula did you apply or which concept did you apply?
BLB sin theta.
VLB sin theta, yeah. So basically V cross B to L. So if you break those cross components, so VBL sin theta. Okay. So see, flux is coming out from the north pole in the air gap from north to south. So this is the direction of flux density or flux, okay, or magnetic field. And the conductor is moving upward in the z direction. So the angle between V and B is given as 90, right? Here from this figure, if you observe, angle is given as 90 degree between V and B. So since angle is given 90, you can directly substitute it by 1. The angle between the velocity of the conductor and flux density is 90 degrees. Hence, you can replace sin theta as 1. Now we are left with VBL. V is given as 5 meter per second. B is given as 0.8 Tesla. And L is given as 2 meter. So 10 into 0.8 will be 8 volt. So Rajesh was correct. 8 volt is the answer. And the direction of the EMF will be in the direction of force. So if you cross your finger from V to B, okay, you place your hand in the direction of V and you curl it towards the magnetic field lines, and you will see that EMF will be equal to, or force will be towards X direction, right? Am I correct, Rajesh?
Yes, sir.
Yeah. So how did you compute the direction from x to y?
By using, sir, Fleming right hand rule.
Fleming right hand rule. Okay. So yeah, that is good, but it's just that you will be confused every time. So instead of Fleming right hand rule, if you are not able to recall what was Fleming right hand rule or Fleming left hand rule, you just place your hand in the direction of velocity of the conductor and you curl it towards the magnetic field, and you will be able to see that force is towards the x direction. Okay. And if force is towards x direction means x, its force will be from y to x, right? It acts in the direction from in movement of the conductor in the direction of x, right?
Y.
Sorry, you are saying x to y.
Yes, sir.
Okay, so okay, let me place hand once again. I am also getting confused. So V cross B, and yeah, so your x terminal will become positive. Let me write. So this is the polarity of EMF. Am I correct? If this is the conductor, and if you are asked about the polarity of the EMF, is this correct?
Yes, sir.
Okay, so it means whatever you applied Fleming left-hand rule, I guess you have very good memories so that you can recall it from class 12 concept, but then it is correct. Anyone has any doubt in this applying Fleming left-hand or right-hand rule or Maxwell thumb rule? Feel free to speak.
Sir, according to these questions, we apply, sir, Fleming left hand rule or right hand rule. But sir, I do not understand, sir, Maxwell rule, sir.
Okay, so see, let me show you. Okay, so to turn on the camera, I have to stop presenting. So just let me basically tell you. You place your palm in the direction of the velocity of the conductor, okay, and you curl your palm towards the magnetic field, okay. So you will be able to rotate your hand by 90 degrees, and then the direction of your thumb will be towards X. Are you getting it?
There is the direction of thumb is towards Y, sir, from X. According,
You are getting your thumb in the direction of Y or in direction of X?
sir, if I put the one palm in the direction of V and
Mhm.
then just hold the all four fingers towards the direction of
Magnetic field.
magnetic field in the
Mhm.
positive x-axis, then my
Yes.
thumb will denoting like from x to y.
How come it be? See. Okay. Let me turn on the camera anyway.
But there is a right hand side.
Okay. So you are using right hand. Okay. Okay.
Sorry, sir.
Okay. Okay. Anyway, these are some things for which we need physical interaction. But anyway, just try to visualize it. Visualize it. So in question 13th, we are required to compute the magnitude of induced EMF, which we already computed from the question 12, which came out to be 8 volt. And I think Ayush or Rajesh provided the correct answer for that problem. And hence we can move to question 14th. Okay. Now, I think question 14th is done. Question 15th. Yeah. Oh, sorry. Mm, yeah. So here, the direction of the velocity has been changed of the conductor, and the magnetic flux is same. The direction of magnetic field is same. So now you need to compute the magnitude of induced EMF in the conductor.
Zero
Are
volt,
you
sir.
0 volt? Yeah, that's correct. 0 volt, because both magnetic field and the direction of conductors is sorry, both of them are in the same direction. So if you apply V cross B, so sine theta is equal to sine 0, and it will be 0. Okay, I hope it was pretty simple. Anyone had doubt in this? Okay, moving forward. In this problem, again, everything you know, you just need to replace the angle of theta as 30 degree and you will get the answer. So anybody could compute it, please, and provide me an answer with
Sir.
Okay, V is 5 into
4 volt, sir.
4 volt. Okay, we will verify it. V L into sine 30. So yeah, it will be 4 volt. So these questions are just to brush up all your electromagnetism concepts. So, and after this, we will go, or we will move to basically transformer concepts and all. So that's why it is, you know, to study the machines concept, you first must be very good with all electromagnetism concepts. So for that purpose, we choose all those problems for you guys. So in question number 16, you need to find out the direction of force. Which direction of force the conductor will experience if such
Towards
current is
upward, sir.
upwards.
Upward direction, sir.
Upwards. So I got upward as a response. So okay. So here I think you can apply that Lorentz force equation. I L cross B Am I right? And if you see, both expressions are same only. So the dimension of I and L is nothing but amps meter. And here also QV, and Q is nothing but, sorry, I into T, current into time, and velocity is nothing but length by time. So you can see that both time will be cancelled, and dimension of QV will also become IL. Okay. So this is basically known as a Lorentz force equation. So now the direction of current in this direction. So we take length vector in the similar to the direction of current, and if you see, if you place your palm in the direction of the length of the conductor and you curl your palm in the direction of magnetic field, then you will be able to see that your thumb will point towards upward direction. So whoever mentioned as upward direction, they are very correct. Upward is the correct answer. Anyone has doubt in this? So that if
Sir,
you have
supply.
doubt,
Sir, supply will be given in a question.
supply is given in the question, but that number is not given. It is just mentioned that a battery is connected to the conductor and current is flowing in the conductor.
Means, sir, supply will be given, but and we can find direction of current. Yeah.
Yeah. Yes, you are correct.
Sir, so I have a doubt. So this question will be solved by using Lorentz force, and the Lorentz force can deliver the current carrying conductor is placed in magnetic field. It experiences a force, and this
Yes.
direction can be determined by using Fleming left hand rule. No, sir.
You can compute it with Fleming left hand rule, right hand rule, or whatever Maxwell thumb rule. Okay, I generally use Maxwell thumb rule here also. I use the same.
Force in these problems, or force will be calculated, not sir generated EMF will be calculated.
Yeah. Here you have to identify in which direction the conductor will experience the force, right? So you place
Yes.
your palm in the direction of current, okay, and you curl your palm in the direction of magnetic field. You see your thumb will point towards upward direction. Are you able to visualize that? Right hand you place, right hand palm you place in the direction of the conductor or current, and you curl it towards the magnetic field. You see your thumb will point upward.
Yes, sir. Yes, upward will be correct. Okay, thank you, sir.
Yes. Yeah, welcome. So I hope it is fine, or if you have doubt regarding this problem, please speak up.
But sir, NPTEL session problem will be sir too hard, but this
Sorry, I couldn't get you. Could you please repeat it? Rajesh?
sir NPTEL session problem sir will be hard. Sir, can you sir help to solve sir this problem?
You mean assignment problems?
Yes, sir. Yes, sir. Yes, sir.
Okay, current week assignment problems we are not supposed to discuss, but anyway, if you have some conceptual doubts, we can discuss about that. Okay.
Okay, sir.
Okay. So yeah, for time being, just complete. First, I will complete this portion, and then I will switch to whatever you have doubt. Okay. So again, in this problem, you need to identify the magnitude of the force that it experiences.
Eight volts, sir.
Newton, sir.
Sorry,
8
how
Newton.
much Newton? 8 Newton. 8
8
Newton. Okay. So again, as I told you, F is equal to I L cross B. Okay. So you just need to apply this formula, and current is 2 ampere into, since the length of the conductor where it is placed, it is orthogonal to the direction of magnetic field, and hence L cross B, you can write it as L into B into sine 90. Okay, so it will be I L B, and I is 2 into length is 5 meter, to B is 0.8, so 8 Newton. Yeah, so you were correct, 8 Newton. Does anyone have doubt in this problem? We can discuss it. Okay, then. So let's move to the next problem. Problem 18th. It is a bit different. Just read the problem for once.
Anti-clockwise, sir.
Anti-clockwise. Okay.
Clockwise direction, sir.
Clockwise.
Clockwise, sir.
Clockwise by Rajesh. And one more, who told?
I use,
And
sir.
Ayush.
Anti-clockwise.
Ayush told anti-clockwise. And one more person responded clockwise. Who was that?
Yes, sir. Clockwise direction, sir.
Ravidas.
Yes, sir. Yes.
Okay, so we will see. Okay, so first, Ayush, you go ahead with your justification for anti-clockwise.
Yes, sir. There is two cases, sir. First, I consider the current is outgoing. Okay.
Mhm.
Then we have put
No, no.
the
Wait. Just a second. Take a pause. Why are you considering any direction of current, since it is already mentioned the direction of current in each wire, each portion of the coil, right? So whatever the direction of current is given, you move ahead with that only.
Yes, sir. I am going with that only. Yes, sir. For clarification, I have just assumed, sir, in mind only.
Okay.
Sir, first I have put the direction, first direction of current, which is outgoing from the conducting wire.
Uh-huh.
Put the whole palm in the direction of current and just move the all four fingers towards the magnetic field. And
Mhm.
my thumb point out towards upward. Sorry, toward upwards.
Okay.
And similarly, we've done the same process
In,
in the same while
just a second. You mentioned in this wire it was upward, right?
yes, sir. Yes, sir.
Okay. And in this wire now you are telling downward.
It downward. Then it feel like it will rotate like
Rotate
anti-clockwise.
clockwise. Oh, sorry. It will rotate in clockwise, no? Oh, okay, no,
And
anti-clockwise. Yeah, anti-clockwise. Okay. And according to you, it is anti-clockwise. Now, Rajesh, you go ahead with clockwise justification. Rajesh or Ravidas, anyone could go ahead.
Hello, sir.
Yeah.
Sir, matlab in this figure, sir, direction of field is given and current is given. Okay.
Yes. Okay.
At the terminal of north side, we can apply, sir, Fleming left hand rule. So then they apply Fleming left hand rule. The middle finger shows the direction of field and the middle finger direction of current and the thumb will be direction of the force
and this pointer will be in direction of
field.
In the direction of field, and thumb will be in the direction of force.
Okay.
Right.
And the other hand south pole direction of current will be given, and the direction of field with force will be downward directions.
Downward. So, okay. So, it according to you, you applied Fleming left-hand rule, and you got clockwise direction of the rotation. Okay. So, actually, by your condition of Fleming left-hand rule, let me apply. Actually, I also forgot Fleming left-hand or right-hand rule, because I generally do not apply Fleming hand rule because I am very much comfortable with right-hand thumb rule. But anyway, you just go back and verify with Fleming left-hand rule whether you are applying correct direction of your thumb or middle finger or pointer, or whether you are applying right hand correctly or left hand correctly. But
Sir, if you right hand thumb rule, you can apply right thumb rule. Okay, now so direction of thumb will be direction of thumb current, and the fingers will apply the force upward, and the direction of current is down south pole direction of current, so the thumb and the force will apply downward. So in this way, so sir, clockwise directions will be find, sir.
Okay, so just hear me for once. You just place your
sir,
yeah.
So as we know that, sir, the motoring of in the case of motoring or motor, we just use the Fleming's right hand rules, not left hand rules.
Yeah,
Motoring,
that's
Fleming
what.
left hand.
Okay, so are you telling that in motoring case people use Fleming right hand rule, and Rajesh told that it is left hand rule, right?
Apply.
Sorry, I didn't get you.
Sir, Fleming left hand rule apply use in case of motoring, because sir, this formula would be derived from the Lorentz force.
Okay.
When a conductor is placed in magnetic field, it experiences a force, which direction is given by the Fleming left hand rule.
Okay, so I'm assuming Rajesh your answer. I'm applying Fleming left hand rule. Okay, I am placing my middle finger in the direction of current. Okay, and I am I am pointing my pointer finger towards the direction of magnetic field. Am I correct? Are you with me, Rajesh?
Yes, sir. Yes, sir.
Yeah. So the thumb will give the direction of force, right?
Downward, downward.
So it is downward, right?
Yes, sir.
Yeah, yeah. Yeah, these things are a bit confusing, but so conclusion is that in the left wire, you place middle finger in the direction of current. Okay. Middle finger you place here, and your pointer you should place in the direction of magnetic field, and you will see that force is in downward. That is the direction of force. Sorry, that is the direction of your thumb. Similarly, if you apply in the right hand side, current direction as a magnetic field, current direction as middle finger, and pointer in the direction of magnetic field. So you can see that thumb will be in upward direction. So here force will be upward. So if this satisfy, then your conductor will rotate in anti-clockwise direction.
Thank you, sir. This question will be clarify.
Okay, great. Still, if anyone has doubt regarding this, you can raise your hand or speak up. Okay, so I'm guessing no one has any doubt related to this problem. So now here comes the next question, and the conductor has been rotated by 90 degree, and you need to identify the direction of the rotation.
Sir, option number A.
Option number A would not try to rotate. Okay, anyone else has any different opinion?
At the sir upper end, force will be upward directions.
Force will be in upper wire, force will be upward direction.
Right.
Okay. Right. So it will remain in upward position, right?
And the lower positions force will be downward directions.
Force will be in downward direction, and it is already in downward position. So I don't think they will try to rotate, right? So if you apply any rule, either Fleming left-hand rule or Maxwell thumb rule, you will see that in the position they are placed already, the force will again be in that direction only. So for this wire, the force will be upward, so it is already upward. So it will not try to rotate the conductor. And for the downward wire, force will be downward direction, so it will again be the same. So both are same. So the conductor would not try to rotate. So as he said, option A is correct. Any doubt related to this?
No, sir.
Okay. So if not, then I'm moving towards the last problem. So read this question and keep your answers with you, and I will take a 2 minutes break, okay? And I will come back in 2 minutes. So Rajesh,
Yes, sir.
did you find out any answer for this problem or any logic? First of all, did you get the question or not?
Option D will be, sir, correct. I think. Like.
Option D. Option D has been picked by Rajesh. Anyone else?
Sir, can I, sir, explain this question, sir?
Definitely. Please go ahead.
Sir, in this figure, sir, direction of rotation is given and a direction of field is given. Yeah, sir.
Yes, yes.
When a conductor is rotate in a magnetic field, in this conductor, according to law of Faraday, EMF will be induced and the circuit will be closed. The current will be flowed because the induced EMF, that is voltage, is always close. Yes, sir.
Correct, correct.
In this terminal BC, we apply the Fleming right hand rule because these conditions will be generated. So then we find the direction of middle finger, and the thumb will be direction of rotations, and the middle finger will be direction of field. Then we apply the current direction BC in from B to C, and the again left side the current we find D to E. D to E.
Okay.
In this way, the circuit will be closed. So, sir, only one options will be, I see the FGHA.
FGHA. Okay,
Yes, sir.
right. So this current will flow through the, yeah. So who is in the favor of Rajesh and who
Yes,
are
sir.
Sir,
opposing
there is
this law?
more than one answer, sir.
Sorry, could you please repeat?
There will be more than one answer.
It may have more than one answer, yes, but I don't think so because in options it is given with only singular option, so it will have only one option, I guess. Let me check whether it has more than
This
one
is
option or not.
multiple selecting choice question, sir.
Okay, then it can have more than one option. So okay, so first thing is, are you in the favor of option D, or do you have any other logic? And then we will check whether other options are correct or not. Okay.
Option D is also one of the all answers, sir.
Option B you were saying, right?
No, no, sir. D. Sorry, E.
E. Okay.
E. My answers are A,
Mm-hmm.
C, A, comma C.
Mm-hmm.
No, D not correct. E will be correct. FGHA. Okay.
My answer is F. Sorry, A, C, E, F.
A, C, E, F. Where it is given.
Yes, sir.
A, C, E, F. You are telling in this manner?
Yes, sir.
Okay. So yeah, whatever Rajesh explained, according to him, option E is correct. Yeah.
Yes, sir.
So option E is correct. Now, yeah, current will flow. If current is flowing in the loop of FGHA, it must also flow in the loop of ABCDEF, right? Am I correct,
Yes.
Rajesh?
Yes, sir.
Am I correct?
Yes, sir. The same current flow through this loop.
Yeah. So option F, which has been picked by Ayush as well, option F is correct. Option E is correct. Now about option A. No EMF will be generated in the coil as the coil is lying parallel with the flux lines. Is it correct?
No, sir, because sir, direction change in flux is maximum, minimum, and the cutting of flux is maximum. So the EMF will be induced when cutting of flux will be maximum. D phi change, because sir, EMF formula is E barabar D phi by dt. So this
Yes, sir.
D phi, this is change in flux. So change in flux maximum at this position. This is given by in a figure.
Yeah. So yeah, of course, current is flowing only when it has some induced EMF, right? Otherwise, how could it flow? So option A doesn't seem to be correct to me. Now, induced EMF will be such that terminal A is positive and terminal F is negative. Okay, so is this correct or not? What about option B? I am discussing about option B now. You have to justify whether it is correct or not.
Option D
From
is
positive,
false.
A is
Option
negative. A is
Mhm.
negative and is positive.
A is negative and F is positive. Okay.
This
Yeah. Yeah. So F is positive and A is negative, right?
yes, sir. C will be like correct.
C will be correct answer. So Ayush, you tell me, you picked both on option A and C, but both are contradicting each other, isn't it?
Yes.
Sir, listen me, sir.
Please.
Just I have assumed, sir, then for first question, just I have assumed that there will be no any EMF if the coil is in the same direction or parallel direction in the flux, because the sin theta is equal to 0 in that
Oh,
condition.
okay,
Just I have
but
assumed that remains all three options will be chosen according to these questions only. Option number A is just assumed, I sir.
okay, no problem. But be careful from if you see such type of problems in exam, do not assume. Go first, solve it, and then pick the option. So we are finalizing and locking the options. So option C, option D, sorry, option C, option E, and option F. Right? So 3 options are correct. If still anyone has any doubt, please go ahead and speak.
Sir, option number A will be not a good statement, sir, according
No,
to
no,
this.
no. Option number A is completely contradicting all other options, isn't it?
Yes, sir, it is contradicting, but we are rotating this coil, na, sir. Then at any moment, this coil will be in the same direction with this magnetic flux.
Yeah,
Then
see, you are correct. You are correct. You are correct. I agree with your statement. But you read this question and you read this word at the instant depicted in the figure. Which among the following are true?
okay, sir. That means we have to choose the answer at this condition.
At this instant only, yeah, according to the question. Such type of mistakes generally leads, generally cost you negative marks in good type of exams. So be careful with
Okay, sir. This is the style of IIT, sir.
that. Whatever they frame in such a manner that people generally fall in their questions. So do not fall. Even you know the concept, you do not fall for their traps.
Okay, sir.
Okay, then. So these were the questions from week 0, and yeah, so someone told that they have doubt from current week's assignment. So which question do you have any doubt? Let me.
Sir,
Go ahead.
sir, I have sir some doubts regarding the sir assignment questions, sir. How can I help you, sir?
Let me present that current week's assignment question. Okay. Windows. Are you able to see my screen?
No, sir.
Okay.
Numbers.
Okay. Could you just tell me the question number? Of current week's assignment question number, if you could tell me, then I can bring that question up and we can discuss it.
So question 8.
Question 8. Question 8, which is a common data type question, right?
Yes, sir.
Okay. Just give me a moment so that I can bring that question on the screen. Are you able to see my screen?
Yes, sir.
Okay. So in this problem, it is basically a common data type question, and we are given with a primary voltage supply. Okay. And we are given with a transformation ratio, and we are given with impedance or reactance and resistance values. We
Sir,
need
can
to
I
add.
sir,
Go ahead. Go ahead.
in this problem, sir, we can, sir, solve the Vs by V out equal to N2 by N1 by N2. This help the output voltage. This is the across of RL we can find, and again from current through the RL will be find. Yeah, and
Yeah,
in this
that
help
is.
the one can also find. Okay.
See, the best method I would recommend you to draw an equivalent circuit diagram. Transfer the secondary side to either primary side or transfer the primary side to secondary side. Okay.
Okay. Yes, sir.
And very convenient in this question is to transfer the secondary side to primary side because there is only one element, that is resistor, load resistor, right?
Yes,
And
sir.
I am sure that you might be knowing the whatever the terms is you need to apply in this expression. If you basically transfer this impedance, if you direct if you draw an equivalent circuit, you need to transfer this resistance. What is happening? Yeah, you need to transfer this resistance to this side, towards primary side, and the resistance will become RL equivalent from primary side. If you see, it will be RL into N1 by N2 a square, isn't it? Then you just connect resistance in series with inductance, and it is nothing but a single phase AC circuit, which you must have studied in network or circuit theory.
Okay.
Then you compute I1. Okay. Once you get I1, how much time it will take to compute I2? Since you know the MMF balance equation, N1 I1 is equal to N2 I2.
Okay.
Okay. And once you know the I2, you can estimate the power.
The power formula will be either Vs multiply I2, or I2 multiply V out.
No, you directly apply na I2 square RL.
I2 square?
RL.
Oh, I2 square RL. This is okay.
Because there is no core loss resistance is not mentioned in the circuit. So you can, whatever power is getting towards the output, that must be supplied from the input. Yeah, go ahead. Anyone is saying something?
Sir, we can also calculate the or estimate the source power supplied from the primary side using the formula of to IS.
Obviously, Vs into I1. You can compute by multiplying Vs into I1. Okay.
Yes, sir.
I hope it is
This
clear.
session will be available for us for future time.
Definitely, this session will be recorded and it will be made available to you guys.
At where, sir?
One thing you can see it at my YouTube channel. I generally upload all my sessions there. That name of the YouTube channel is JDS@IITB. Okay.
Jade.
So you can J Jitendra
Thank
J
you,
for
sir.
Jitendra JDS@IITB. This is my YouTube channel. So I will upload there. You can find me there. Or otherwise you will get a mail from NPTEL side, or you can find the recording in this Teams channel as well.
Sir,
Yeah, go ahead.
Sir,
Sir,
can you,
Uh-huh.
sir, can you please schedule the class from 5:30 to 7:30?
Now this scheduling is very much difficult because it is not in my hand. Sorry, could you please turn off your mic because sound is getting echoed. Yeah. So I was telling that it is not in my hand. It is completely in NPTEL authority that they have decided once and they will not be able to change it. I can understand that you are not able to attend this session, but try to attend all other session and join it at 6 p.m. And anyway, you will be getting recording lectures, right? So try to compensate that 30 minutes with the recording lecture and join at 6 p.m. And we can go till 8 p.m. So at 7:30, do you have any other class or something?
No, sir, because I am living in my college hostel, and so my mess will be closed by 8 p.m. It will start from 6:30 to 8. After 8, it will strictly close. They are very punctual. That's why
Okay. So sorry about
my
that,
college
but
mess.
no, why are you just made your point. So I'm sorry I couldn't reschedule, but I will see what I can do. In the meanwhile, you can compensate it with recording lectures, and we can see what we can do. Okay.
sir,
Go ahead.
sir, in assignments, sir, 12 number questions. How can I, sir, solve, sir? Please, sir, say.
Okay, 12th number question. Let me bring that. Just give me a couple of minutes. I will be ready with that. Yeah. So
Okay,
I
sir.
hope you are able to see the problem. Your doubt is related to 12 number question. First, we will read the problem and then we will go towards the approach. Okay, so primary winding have some terms and it need to supply towards secondary and tertiary.
Sir,
Mhm.
in which,
Go
sir,
ahead.
primary I2 and I3 will be calculated first. So this is solved by the MMF balance because N1 I1 barabar N1 N1 is equal to N2 and N or I2. And again we can calculate it N1 I1 is equal to N2 N3 I3. In this process I3 and I2 is calculated. Am I right?
Yeah, from the transformation ratio, you can compute I2 and I3. That is true. Okay. And now the RMS value of supply voltage is required. So see, uh, that supply voltage, you can compute it from the power balance. Whatever the power is required to supply the 100 ohm resistance and 50 ohm resistance, since you have already computed I2 and I3, right?
Yes, sir.
If you have computed I2 and I3, and now you know the load power, you just equated them to source power. Okay.
Yes, sir. Yes, sir.
And you know the source current, you just need the source voltage that you can get it from the equalization.
Okay.
Okay. Okay then. So I hope this is all. We are on time. If there is no other doubt, we can wrap up the session. So I will try to upload the video recording, and I will see you all guys on next Sunday at 6 p.m. Okay. Bye bye.
Okay, thank
Good
you,
night.
sir.
Thank you. Bye bye.
Sir, how long will it take for you to upload this?
Sorry. Okay. How much time it will take? By 9 p.m. it will be up on the YouTube.
Okay, sir. Sir, actually, we receive mail regarding like we have 2 to 3 classes in the week. Will all the classes will have the same content? I mean, like attending one session is enough?
Okay, so all the 3 sessions will have the similar content because we are restricted to discuss only up to week's lecture, whatever you have been taught. Okay, so those will be similar, but I am not sure that all the contents will be same because honestly, we do not generally discuss among each other that what actually we do not know also each other. So I don't know what they will be teaching, but content boundary will be same, but you know, uh, I can't comment on the nature of content. Is it okay?
Okay. Yeah, sir, thank you.
Yeah, thank you. Okay, everyone. Thank you very much for joining this session. Bye bye. Have a great night.
Thank you, sir.
Thank you.